Мгм. Ну, вас пока немного, я думаю, что можно пару минут подождать. Виден ли экран? Мгм, хорошо. Ну ладно, давайте начинать. Эм, Сегодня речь пойдет о сверхпроводящих кубитах, о которых мы с вами говорили и в предыдущих двух лекциях. So, according to our strategy, multiple time discussed, I switch to English, but questions in language you prefer are welcome. So, at the previous lecture, we started talking about circuit QED, which we will bring up again number of times. And we also started discussing transmon qubits, which are the working horses of nearly all modern superconducting quantum processors. So today we'll continue a little bit about talking about transmon and QED, discuss briefly 3D QED, and then talk about other types of qubits. So let's remind again what is a transmon. So as you remember, transmon is simply Josephson junction, which is shunted by capacitance, making its charging energy significantly smaller than the Josephson energy. And with that said, the potential in the phase space is going to be a cosine. So again, it's not a tilted cosine, what we discussed for phase qubits, but rather just flat cosine. So having multiple minimum, which are equivalent, of course. Change of phase by 2 pi doesn't change physically anything. And the parameters are such that the effective mass of this quantum degree of freedom is such that the quantization of the energy levels gives us eigenstates, which are only few, between 7 and 10, so to say. So the potential is anharmonic. We can approximate it by this polynomial form, having the second order term proportional to the fourth power of the phase. Now this phase here, which you see at the bottom, and the phase up there is the same. It's just a different formula. Excuse me. And then the energy difference between the ground state, which is here, and the first excited state, which is the second level here, is roughly 200 megahertz larger than the energy difference between the first excited and the second excited state. And this is characterized by the parameter which is called anharmonicity. We denote it as alpha in absolute units. And it turns out from the properties of the transmon Hamiltonian and eigenstates which we discussed in the previous lecture, approximated by Matthew functions and so forth. The unharmonicity parameter is pretty much exactly in the second order perturbation expansion is given by the charging energy. So roughly the energy separation between the ground state and the first excited state is determined by the Josephson energy and capacitance, and then the unharmonicity is determined solely by capacitance, which is the charging energy E squared divided by 2c. So all that is discussed in this very relevant paper, which is a theoretical paper proposing the transmode and calculating all the eigenstates by Jens Koch, which has all these approximations and all the formulas I discussed before. And I told you that this device quickly became the device of choice between physicists and experimental groups which were developing superconducting qubits. About 10 years ago, it was, maybe 12 years ago, it wasn't obvious, but then like 10 years ago, it became really completely obvious that this is the qubit of choice because of the simplicity, because of robustness in terms of properties and frequencies, universality of this unharmonicity parameter, at least relative harmonicity, which is alpha divided by energy level separation 0,1. And then I told you that typical geometry which people favor now, or many people favor now, is the cross-shaped electrode, which is sometimes called XMON, after the work of the group of John Martinez at UC Santa Barbara. And here you have metallic electrode in the middle, and then at the bottom you have a Josephson junction here, which consists of two Josephson junctions forming a squid. So this is a composite Josephson junction. And the Josephson energy of this composite junction forming a squid is controlled by the magnetic flux produced by current, which is sent in this middle wire at the bottom, and then extracted to the ground to the right. So this current generates magnetic flux in this loop, which contains two Josephson junctions, and the upper electrode, which is this blue fragments which you see on the right insert. And then you control this device in this two-dimensional geometry by applying pulses to the electrode on the left, which is basically a capacitively coupled line, which allows to control, depending on the phase, rotations around x-axis and y-axis of Bloch sphere. Naturally, from the nature of Hamiltonian, the rotations around z-axis are controlled by this flux, which can be also done quickly. It's not just DC line, but the line which can transmit a few nanosecond long pulses. And then the upper end of the cross is used by to couple the qubit to the resonator, which is used for readout. And the resonator in turn is coupled to the transmission line, where you send microwave tone, and then at the frequency of the resonator, one observes a dip. And this dip shifts in frequency if the qubit state is changed from 0 to 1. So if you go from ground state to the first excited state. So this allows you to read out the qubits. And as I told you, also naturally, this frequency depends on the length of resonator. So it's feasible to use multiple resonators at different frequencies, coupled to the same readout line to read out multiple qubits. So typically, people use 8 to 10 qubits at maximum. And the reason is the limited saturation power of the preamplifier, which we will discuss a bit later, the so-called parametric amplifiers used in modern quantum architectures. And finally, the quantum bus, which you see on the right, is the way to couple this qubit to other qubits. So this could be a resonator type coupling, which is possible, but then the gates are rather slow. But we'll discuss specifically various schemes for 2-qubit gates in one of the following lectures. All right, so this is the two-dimensional transmon, which is scalable and is used in all modern architectures of chips for quantum computing. Now, few years later, after the transmon was proposed, after this paper by Jens Koch, published in 2007, only a few years later, there was a very surprising, the first moment was very surprising discovery that one can use these transmons in a different architecture, actually in a three-dimensional environment. And moreover, these transmons, which are rather big, which can have size of millimeters, they have extremely long coherence times. At least to that time, 10 years ago, these times were record times. They were in the range of 100 microseconds. Nowadays, material improvement and experience of many labs which fabricate superconducting qubits brought also two-dimensional geometry also to the range of about 100 microseconds. But meanwhile, the three-dimensional geometry was developing as well, and now 3D transmons have coherence times of the order of a millisecond. The three-dimensional transmon is extremely conceptually very simple device. Imagine that instead of planar resonator, which I showed you before, this resonator is this widening line where my pointer is. It's just frozen now. I cannot move it for some reason. But anyway, this is this readout resonator in two-dimensional geometry. In three-dimensional geometry, we have a three-dimensional resonator. And in 3 dimensions, there is no dielectric. So in 2 dimensions, you have a substrate, you have typically silicon, which has dielectric loss. In 3 dimensions, you just have vacuum. And vacuum is just empty space. It doesn't have any dielectric loss. So the only loss which occurs is at the surface of the box which surrounds this cavity. And the 3-dimensional transmon consists of aluminum block, which is prepared in machine shop, basically cutting here a hole на фрезерном станке, which has a particular dimension, has particular modes of this cavity. So, of course, the 3-dimensional cavity have multiple modes corresponding to the quantization in different directions. So one has to solve the problem of finding the eigenfrequencies by solving the Maxwell equations for the cavity, finding eigenvalues with the boundary conditions determined by the size of the cavity. So the loss in the resonator is small. That's one thing. But also in the qubit, it turns out that the losses in the qubit and the coherence times are predominantly determined by the loss in dielectrics on the surface of superconducting films. The physical mechanisms of this loss we are going to discuss next week when we discuss two-level systems, two-level defects in qubits. However, here, basically the idea is to open up the capacitance, which was like this, sort of having pretty closely positioned metallic electrodes in 2 dimensions, and therefore quite high amplitude of electric fields in this in the gap between the electrodes. Here you open up the electrodes, the capacitance drops down. So to come to the same value of capacitance, you need to increase the area of metallic electrodes. You need to make the metallic electrodes larger. But the electric field, which is, of course, the oscillating electric field, once you have transmon operating, you have basically oscillating current up and down of different amplitude, depending on the particular state which you excite. So for the ground state is the smallest oscillation. For the excited state is next smallest, and so forth. And the oscillations which occur, they will generate AC electric fields also on the surface of superconducting electrodes.
But due to the large distance between the superconducting electrodes, the magnitude of this field is going to be at least 1 order or more smaller than it is in the planar two-dimensional geometry. And this idea turned out to be extremely productive. So basically, having the qubit, which is a single Josephson junction, it's not practical to use here SQUID, because the qubit is surrounded by a superconducting box. You cannot really apply magnetic field inside superconducting box. Therefore, people mostly use here fixed frequency transmons, so just one Josephson junction and 2 large electrodes of the size of about millimeter give the right capacitance there to operate this at the frequency, let's say, between 4 and 8 gigahertz. So this device has no inductance. It has large capacitance due to this large electrode. It has low electric field intensity, and therefore it doesn't really excite as much defects as two-dimensional transmons do. And it avoids dielectrics. So basically, replacing vacuum, by vacuum, the lossy dielectric makes the energy dissipation very low. And then here you have basically two, in the geometry on the left, you see here, you have 2 lines. One line you could send the signal in, the other line you can send the signal out. Or you may eventually use the same line and then use 2 microwave tones. And what you do, you basically use one frequency, which you apply over one line as a readout tone. It will be close to the frequency of the cavity. And if the cavity frequency is shifted by exciting this 3D transmon from ground state to the excited state, then there will be a change of the amplitude and change of the phase of the signal reflected from the cavity at the frequency of the cavity. And the second tone, or the second line, which can be installed here, is simply used to manipulate the qubit. So the qubit has a frequency which is very different from cavity, can be factor of 30–40% different from the cavity. It has to be different from the cavity because if the qubit has the frequency of the cavity, it will, of course, be provoked to relax emitting a photon in the cavity, which is called Purcell effect. And therefore, you need to be not Purcell limited. You need to detune the qubit, or to make the qubit of the frequency which is far away from any modes of the cavity. But because the dipole moment of the qubit depends on the state of the qubit, this little change of the electric dipole moment of the qubit shifts the frequency of the cavity, which makes it possible to read it out. So this is how this device works, and it is being used for variety of beautiful experiments, mostly studying physics of these devices. Due to the high coherence, they were very productive, but also being used for cavity QED, which I will mention very briefly in the next slide. Now, this slide shows you an example of this 3D transmon. So you see a physical picture of this big cavity, which has in one dimension size of almost 40 millimeters. And that means that half wavelengths at 40 millimeters is going to be corresponding to something like 8 centimeter wavelengths in vacuum. So it's roughly a frequency of maybe 12 gigahertz or so for the readout. And then the qubit is located here at one of the nodes of the electric field to be able to couple to the cavity frequency. And therefore, this qubit is simply 2 bulk electrodes, which you see here, with a little Josephson junction here in the middle, which is not visible because it's very, very small. So smaller fields which are occurred here are compensated by choosing a larger dipole moment for the qubit, and the dispersive shift can be as large as tens or even hundreds of megahertz, depending on the design. Now, just to sum up about transmons, what makes the transmon so good? First thing is the transmon is shielded from external noise sources by the resonator. So this resonator actually acts as a narrow band pass filter. it turns out that in practice, people use not only one resonator, but two resonators connected in series. And one of them is called Purcell filter, which cuts the frequencies of the second order filtering of the first band of the first filter band. But this is kind of design which we are going to discuss maybe a bit briefly later on. So it's coupled to resonator, and this resonator acts as a narrow passband filter shifted away from the frequency of the qubit. Therefore, the qubit, when it's detuned, the energy relaxation in the qubit is suppressed by the Purcell effect. So the photon emission doesn't happen because there are no available free states for the photons in the environment inside the cavity, away from the cavity frequency. Now the capacitive shunt is very large, and therefore the charge noise is very strongly suppressed. Finally, of course, the coherence time is very long, and therefore can be used for practical applications. Any questions to 3D transmon, please? Какие-то вопросы? All right. Next thing which we are going to discuss is a different type of qubit, which many people, including myself, now believe to be the qubit of the future, which will have significant advantages over transmons, but it doesn't come for free. So this qubit is more complicated in terms of its level structure and also in terms of physical properties. So this qubit is essentially very similar to the flux qubit, which we already discussed, but it's more general and more robust in terms of changing its parameters. Let me remind you that in the lecture one before the last one, so the first lecture of last week, we discussed the flux qubit, which consists of 3 Josephson junctions connected in a loop. And here, one junction is the quantum junction, which has the dimension factor roughly 0.7 of the size of 2 larger junctions. Now, this is a generic device, but nothing really prevents to make here not 2 junctions, but maybe 3 junctions or even more. And going from this device to Fluxonium is simply making the number of junctions which will occur here on the right, which determine the inductance, the kinetic inductance or Josephson inductance of the loop. This number is rather high. It can be tens and even hundreds of those junctions. So more generally, the picture which you see here, this is the flux qubit, which has 1, 2, and 3 junctions. And on the right, you see geometry of the Fluxonium, which has a more complicated structure. You see this kind of tree or the tree type structure. So the junctions are actually these long bars where you have the overlap between the 2 electrodes, and the connection here is quite small, narrow wire. And the reason is satisfying the goal of minimizing the stray capacitance of those junctions. It's one of the geometries. Actually, there are also much simpler geometries making the series array of junctions like that. So schematically, again, we see here on the left, we see the flux qubit. And on the right, we see the device, which is more general type of flux qubit, which commonly is called Fluxonium nowadays. Now, in the case of flux qubit, you have the 2 energy minima, which corresponds to a small change of the phase. Remember this 2-dimensional profile, 2 phases, phi1 and phi2, and then you have maxima and minima. And I told you that if you go along the diagonal, there is a very shallow minimum, which occurs along this diagonal, actually two minima with a little barrier between them. And if you go from one state to another, then the change of the phase on the junctions is quite small. It's much smaller than pi, or even much smaller than 1, because the barrier is very low and the distance in the phase space is very short. Now, for this device, for the loop, we can always write the flux quantization condition, which is this one. So the sum of all three phases here, plus the complementary phase, which is induced by the external magnetic flux, which is indicated here by phi, has to be a multiple integer of 2 pi's. For the fluxonium, the same flux quantization condition holds. However, while for the flux qubit, this n is conserved, for the fluxonium, this n actually is varied by 1 if you go from one minimum to another. So, and this is achieved by making the junction here quite small, and therefore making its quantum tunneling more probable, so to say, so that the states in this potential are coupled by strong tunneling matrix element amplitude. So here basically you go between the states which correspond to different n, and here you go between the states which correspond to the same n. This is essentially the difference. One can also say the following, that for the flux qubit, basically there is no change of the winding number here. Therefore, there is the phase on this junction never changes by, this junction is never rotated by angle 2 pi. If you imagine pendulum is rotating by 2 pi, making the full turn. While here, if you go between one state and another, localized states in the minimum of the potential, then the phase changes by 2 pi. And this means that this junction actually rotates all the way around its axis in mechanical analogy. All right. I remind you what is this three-junction flux qubit, just to make what I said you more explicit. This slide we already had. So we have the equation for the three phases, then we extract the third phases, assuming n equal to constant, and then we go along this diagonal, and then you have these two local minima, where you actually have a double potential, which is indicated below here. So one minimum is that one, is this minimum, and this minimum is actually here. Now, this is achieved by choosing the parameter of the junction area such that this coefficient, also here called, okay, apologize for the same coefficient as an harmonicity of fluxonium, it's alpha, but it's a different alpha, of course. So it has to be between 0.6 and 0.7. Now, the operation of the three-junction flux qubit, as you remember, was done by describing it as by this corresponding Hamiltonian of the two-level system, and then the potential is symmetric once you have the flux which is applied to the to this loop equal to half flux quantum. Then the energy of the ground state and the energy of the first excited state are rather close to each other, which is due to very large unharmonicity of this to double potential. So it's very unharmonic, and therefore the energy level separation between levels 0 and 1 is much, much smaller than energy level separation to any of the higher levels. The device which actually operates here in the three-junction flux qubit is shown here. It's again schematics of this device, and if you have the situation here at half flux quantum, then potential is symmetric. If you go a bit to the left, then one of the states clockwise current becomes lower energy state, and anti-clockwise current becomes the excited state. If you go in the opposite direction, then it's other way around. So the anti-clockwise current becomes the lowest energy state, and the clockwise current becomes the first excited state. So if one takes into account the higher levels, then you see that actually in this condition, this is a zoom in this very narrow frequency range. And this is a calculation for the case when the Josephson energy is roughly 10 times the charging energy. So you see that the charging energy of these junctions is roughly order of magnitude smaller than for transmon, but one has to take into account also additional disinductive energy, which we already discussed. So generally speaking, now if we make an abstraction of this flux qubit and consider that what we do here, we simply put an inductive shunt to the junction. So generally speaking, any superconducting qubit, knowing about transmon, knowing about flux qubit, knowing about charge qubit, can be sketched as a parallel combination of a Josephson junction, which has its Josephson energy and its own junction capacitance. And then in parallel, you may have either capacitance, like you have for transmon qubit, or inductance, or both. So nothing prevents of having both. And therefore, one has to take into account the three energies which are characterizing this generic circuit. The first energy is the Josephson energy, which is the critical current of the junction times the flux quantum divided by 2 pi. So it determines the amplitude of the cosinus potential. The second energy is the charging energy, which is proportional to the square of the charge divided by twice the capacitance. And here the capacitance actually is the sum of the two capacitances, but if Cj is much smaller than C, then one can simply use this C of the shunting capacitor. So this this value, charging energy, determines the effective mass of the degree of freedom, which we quantize, and therefore we basically determine here the energy level separation. So small is the capacitance, large is the energy level separation. And finally, there is another energy which we did not discuss yet. This is the inductive energy, EL, which is a square of flux quantum divided by 2 pi, divided by the inductance. So basically, by shunting the Josephson junction by inductance, now we should remember, we sum up in the Hamiltonian the cosine and parabolic potential. We discussed this already when we spoke about the modified phase qubit, that you have superposition of the cosine and parabola, and then depending on the amplitude of the cosine and the steepness of the parabola, you may have either just some distorted parabola, or you may have a cosine with a slightly rising potential to the sides, or something in between, maybe parabola which has only 2 local minima at the bottom, but no other metastable states. So fluxonium goes in such direction that actually this inductance is large, and therefore the parabola is very, very soft. So it's a cosine potential which modulates very softly rising parabola. And in this case, you have multiple metastable states. So here you have the energy level separation, or energy potential and structure of levels for an abstractly chosen qubit, such that you have a junction shunted by an inductance. Now, this inductance, as I said, of fluxonium can be a chain of Josephson junctions, but it doesn't really matter for electrodynamic properties. It's just an inductance. And making many Josephson junctions, you make this inductance quite large, and therefore you superimpose cosine, which was this oscillating function here, with a parabola. And then you may have then states which will be extending over multiple potential wells. And then depending on the flux which you apply, here you see zero flux, you have exactly minimum, lowest energy minimum at zero phase. However, if you apply half flux quantum, then you have 2 symmetric minima, similarly to flux qubit. And therefore you will have energy level degeneracy here, which is lifted by tunneling between the 2 wells. And finally, if you go then back to some other states, these are different parameters here on the C. So then you have also states where you have tunneling also between 3 wells. So all these ranges are possible. Here you see that actually this A, B, C, and D correspond to different ratio of the energies. And one has to watch here not only the ratio of the Josephson energy to the charging energy, which we already discussed for transmons, but also the ratio of the Josephson energy to the inductive energy. And all these three plots are chosen here for this ratio being equal to 50. And below you have a variation of actually energy levels going to larger and larger ratio of EJ to EC. So you start going from roughly charge qubit, which is shunted by inductance, to more and more transmon-like qubit, which is shunted by large inductance. But if you go to very large inductances and large ratio of EJ over EC, then the tunneling matrix element becomes smaller and smaller, and therefore you have then not really the convenient frequency level separation between the levels of consideration. So by shunting the charge qubit by large inductance, one avoids low frequency noise, charge noise, which occurs in charge qubits. At the same time, this inductance forms a rather high impedance at high frequency, and therefore this qubit, which is shunted by large inductance, is effectively a charge qubit which is protected from charge noise, not by charge dispersion engineering, which is the transmon, but rather due to the low frequency shunt formed by large inductance containing many Josephson junctions. So this sort of philosophy of going from a single junction qubit to the loop base qubit. Okay. Any questions to that? Okay, let's move on. Now let's talk specifically about fluxonium. So I told you that fluxonium is a device which contains basically a small Josephson junction, something which is known from charge qubit, or slightly larger junction than charge qubit, but the junction is shunted by a large inductance. And the first prototype of the fluxonium was made in Yale, and it was actually started first in the thesis of Vladimir Manouchian, who is very successful graduate of FISTech. So he did his bachelor in FISTech and then went over to do his PhD in the US, working at Yale University in the group of Michel Devarey. So here you see the fluxonium, which is this little junction, and then the chain of a series connected larger junctions. At the right, you see zoom in this area here. Then on the left side or upper side, you see a winding line here, which has a basically a certain length, and it has also mutual capacitance between the two electrodes. So this line forms a resonator, which frequency is determined by this capacitive gap between the electrodes and also the length of the whole line. And then this resonator is coupled capacitively to the qubit islands, and also capacitively coupled through these gaps to coaxial cable coming from the left and then going to the right. Now the resonator is, we know already that resonator is very useful to read out qubits dispersively. So basically this resonator is a dispersive readout for this device which we see in the middle of the picture. Now this particular example, which was a realization of the first qubit in his thesis, was the number of junctions of about 40. The ratio of the Josephson energy to charging energy was slightly larger than the charge qubit, it was 3.6. And then the Josephson junctions, which were present here, they were having the Josephson energy, which means the area basically, a factor of roughly 30 larger than the area of the Josephson energy of the small junction. So these were basically the inductances, and this was the quantum degree of freedom. As I said, the reason of using this inductance initially was thought to be the trick to avoid the low frequency charge noise due to the random charges which are moving on the substrate and fluctuating there at any temperature. They are present there due to contamination of the surface, due to the charge traps and many other reasons. All the reasons for these charge traps are not really known. Many proposals have been made, but only few of them verified experimentally. But anyway, since the inductor is a superconductor, in particular its impedance at very low frequencies close to zero, this makes the potentials induced by these random charges cancelled on both sides of the junction, and therefore there is no offset charge noise. Now, there is also advantage here that at high frequency, which means at the frequency of the level transition between the states of this small junction, the impedance of this very large loop, due to its large inductance, this Josephson inductance, which is not geometrical inductance, but Josephson inductance, its impedance is very, very large. And if, in particular, one makes this impedance larger than the resistance quantum, which is h bar divided by 2e square, 6.5 kilo ohm, then it turns out actually there is a fundamental kind of reason for having protection against of phase winding on small junction due to the effect of the environment, because it's very large inductor. The impedance of that inductance is very large at high frequency. So basically, the junction behaves as a charge qubit, which contains the kind of protection at low frequency, and at the same time, the relaxation between the levels 0 and 1, 1 and 0, is protected by very large impedance of the environment at the frequency of this transition between the levels. So a very clever idea, which was followed up later on by many groups, including my group at KIT and also our group at VSIS in Russia. So here you see the picture of particular energy levels for the parameters which I have shown. So if you have zero flux applied, then as I said before, you have a single minimum at zero phase. And then there are two states, metastable states on left and right, which are separated by a distance of roughly 4 pi in this phase space. Now, superconducting phase difference space, in phi space. Now, if you go to the flux roughly 1/4 of flux quantum, then you make this potential asymmetric. But then there are low energy states, one of them a bit lower than the other, and there will be, of course, separation between those states, which is due to diagonalization of this complicated shape of the Hamiltonian. And then if you diagonalize Hamiltonian for the flux, external flux equal to half flux quantum, which is, of course, you control this by external magnetic field, then you have two lowest energy levels being very anharmonic, very small separation, symmetric double well, and then the upper state, similarly to flux qubit, is somewhere up there. So the result of diagonalization of the three lowest eigenstates in the Hamiltonian is shown here. So you start from zero flux, and then you have no, wait. No, this is the something is wrong here. No, it's correct. It's not, what is written here is not correct. So these are not three lowest energy levels versus flux, but separation between the lowest three pairs of energy levels. So blue line is separation between 0 and 1. Orange line separation between 1 and 2, and green line is separation between 2 and 3. And you see that if you go to half flux quantum, then the energy level separation, as shown on this very left picture above, is very small, while the energy level separation to the high state is very large. And then there will be also yet another state somewhere here, not shown on this picture. And if you vary the flux, for example, reducing it from half flux quantum to 0, then the energy levels change accordingly. And then you have here the frequencies of the levels being quite high. You see that for the symmetric flux, there will be two energy levels very close to each other due to the tunneling between the next second neighbor minima in the potential. All right. Now, this is again the wave functions, the states. Now, the horizontal level of the lines which you see is corresponding to the eigenenergies, while the profile which you see here are the probability amplitudes of different states. So you see the probability amplitude for the lowest energy state is simply maximum here in the middle. Of course, it extends also inside the potential wall because it's a quantum behavior here. Whereas for the high states, you have something which is similar, partially at least, to harmonic oscillator. Any high energy states will have character of multiple high modes, resonances in the cavity. And then if you go to the symmetric potential half flux quantum, then very similar to the flux qubit, you have the symmetric profile, symmetric wave function, and the antisymmetric wave function here. And these are the two lowest energy states corresponding to the lowest energy and the first excited state in this potential. And then also corresponding high states, which are also indicated here. Of course, diagonalizing this Hamiltonian can be only done numerically. And this is, this is done, of course, very quickly. You should remember from your course of quantum mechanics how to do this, basically finding the eigenstates of the Hamiltonian for the stationary Schrödinger equation. This is now the situation when the fluxonium, which is this device schematically shown here, is inductively coupled to the readout resonator. Now we consider not only naked fluxonium, just not coupled to anything, but rather consider the scheme which I already introduced here. We consider this scheme where you have fluxonium device and it's coupled to this readout resonator, which is positioned here on the upper part of the plot. Now, this readout resonator, of course, the system which is equivalent to a harmonic oscillator, which will have equidistant energy levels. And these levels are shown here by the blue lines. You see those blue lines. This is the lowest energy state at about 7-something gigahertz. This is the first excited state at about 14 gigahertz. And there is another one excited state at 21 and 28 and so forth. So this harmonic oscillator. Now, this little inductor, which is sitting in the middle, couples two quantum systems. It couples this harmonic system on the left, which has equidistant energy levels described by these blue lines, or shown here by these blue lines. And it couples then to anharmonic oscillator, which is our fluxonium device, with a kind of soft parabola superposed with a cosine. And the diagonalization of the states of the parabola is shown here by these lines. You see this orange line, then you see the green line, and then you see also the red line, and so forth. And then by seeing here crossings of the different energy levels, intuitively already from quantum mechanics, you would guess that the coupling between the two systems, between the harmonic oscillator and non-harmonic oscillator, a qubit, will generate avoided level crossings. And this basically tells that here you have avoided level crossing in the region of the crossing of the levels, on the condition that this inductance is smaller than the inductances of the two parts, but it's actually non-negligible. So if one makes the picture with not the common inductance, but with the mutual inductance, which is a bit more bulky calculation here, then clearly that making the mutual inductance between the two loops to zero will, of course, remove completely the avoided level crossings. There will be pure crossings. The systems will be not coupled, but once you make the mutual inductance non-zero, then the degeneracy is lifted, and there will be avoided level crossing at frequency, which is corresponding to the coupling strengths. So, and as you see here, you have different states corresponding to different number of photons in resonators. So these are the states corresponding to now here a number of photons in resonator is this blue line you see here. The blue line is the absence of the qubit. Once you have the qubit, then you will have this state here where you have one excitation in the qubit and multiple photons in the resonator. And you see that it has also the orange line going above. This is a so-called dress state. So by coupling the cavity to the qubit, you form the dressed ladder where you have basically the qubit states scaled up by different energy levels in the harmonic oscillators. And then if you go to the state 2 of the qubit, this is green line here, you observe that you have again different multiple states in the resonator. This is the lowest energy state of the resonator with 2 excitations in the qubit, and actually second state excited in the qubit. And this is exciting the second excited state of the resonator together with the qubit. And this picture doesn't really take into account, of course, the avoided level crossings which I described, but that's something which you observe in experiment later on. Now, this is an example of real measurements on this qubit. And already in this plot, you observe that at the frequency of the resonator, this is the resonator frequency here, the lowest energy state of the qubit comes up at 0 flux, and then it crosses the frequency of the resonator. And you see that at the crossing point, there is this avoided level crossing, which is a kind of strong coupling state of a cavity and a qubit when they have exactly the same frequency, and then the degeneracy is lifted, and there is a lower energy state, a little lower energy, and a bit higher energy state at a bit higher energy. And by using this resonator at a frequency which is detuned, for example, you go to the frequency to the state with 0 flux, then the resonator is strongly detuned, but nevertheless, the excitation of the qubit due to existing coupling will still be shifting the resonator dispersively, so one can use the resonator for the readout. Now, these are real data taken in experiment, and then if you measure the, if you basically compare this with diagonalization of the full Hamiltonian, then agreement is really very beautiful. So you observe that the transition 0-1 has this this shape. So at 0 flux, it has the highest frequency, about 9 gigahertz, and then goes down to very low frequency at half flux quantum, which is not shown in the middle plot. And then the transition to the second state of the qubit is shown by this 0-1. So this is this transition here, as indicated by this middle line, and 0-3 is up there, and so forth. I don't really remember what is this SR, but can look it up. I think this is probably one of the rest states in the system, can be obtained by diagonalizing the coupled Hamiltonian. Now, if you go to half flux quantum, a very particular feature of fluxonium qubit is the very low frequency of the transition between the ground state and the first excited state. Now you see here the transition 0-0, no excitation in resonator, no excitation in the qubit, to the state when qubit is excited and resonator is not excited. There is also another transition which is mirrored with respect to the frequency of the resonator, and this is a transition which corresponds to dressing the qubit states with resonator modes. So you go from the excited state of the qubit to the excited state of the resonator. So you basically swap the excitation between the qubit and the resonator, In this case, the frequency is slightly lower than the frequency of the lowest mode of the resonator. And then you have also another excitation where you have basically transition between 0 and 0 and 1 1 state, which will be kind of mirrored low 1 0 0 1 transition, mirrored with respect to the frequency of the resonator. So this is this state here. So when one observes the coupled system of a qubit and resonator, one should be always very careful in sorting the transitions, because at very low power you excite the transitions which are allowed in the first order, but if you increase the power, then you unavoidably also excite transitions which are existing in the second order, have smaller matrix elements, but nevertheless a large power of the applied radiation will make those transitions visible. So this is one of the features which makes the fluxonium rather complicated. So as you see, the energy level structure is by far more complex, by far more dependent on external fields. Now you see the horizontal axis is the external flux, basically the external magnetic field. Excuse me. So so basically it's rather complex, but nevertheless very unharmonic system, which has many advantages over transmon, in particular in terms of the accuracy of the gates which can be achieved with fluxonium. Now let's talk about the properties of this inductance, which we already mentioned. Now you see the practical device in a bit different geometry. So this is a series array of junctions which is extending from this point along this line to this point. So this is a series array of junctions here. And here you see the setup of measuring the fluxonium in the three-dimensional cavity, which I discussed earlier today. This is a small junction, which is located right there. And then on the right here, you see the additional resonator, which is a coupling antenna. So this antenna actually is needed to increase the dipole moment of the fluxonium, which is coupled to the field in the three-dimensional cavity. The frequency of this antenna is, of course, different from the frequency of the transitions in the fluxonium, but nevertheless, it can be also observed as a coupling mode to the three-dimensional cavity. But its role is basically to couple the electric fields of the cavity into the fluxonium through these coupling fingers. And then right in the Hamiltonian for fluxonium will contain the terms associated with the charge qubit. These are these terms with the inductive term and with the capacitive term. So all the three terms like junction, shunting capacitance, and shunting inductance are included in this shape of the Hamiltonian. And then if one diagonalizes this Hamiltonian with these particular parameters, then the energy levels which occur there will have characteristic transition frequencies. Now the characteristic times which were measured in this particular experiment, which is shown here on a few years ago in the group of Vladimir Nucharyan, but he already moved at that time to University of Maryland. The coherence times were of the order of several hundreds of microseconds, both T1 and T2. The transition frequencies in the favored point where the flux applied to this loop was exactly half of flux quantum were very low. And this is one of the advantages of the fluxonium, that instead of upconverting the digitally generated pulses forming the single qubit gates, like if you want to observe Rabi oscillations, you need to apply fraction of the resonant pulse of the transition between 0 and 1, and then you will rotate the qubit on the Bloch sphere. Now, if you do it on transmons, the frequency is roughly 10 gigahertz, and technically, it's impossible to generate a digital profile at this very high frequency. So what people use there, they use the upconversion in frequency. So they have some local oscillator and the mixer, and this mixer is modulated by the digitally generated signal in the band roughly from 0 to 1 gigahertz. And then this frequency is added to the frequency of the local oscillator. So this pulse is basically up converted to roughly 7-8 gigahertz. For fluxonium, which has a frequency of transition between 0 and 1, around half flux quantum, this frequency is of the order of between half gigahertz and 1 gigahertz. One doesn't need to do this up conversion, which is needed for transmode. And therefore, life becomes very, so to say, experimental life becomes very simple. One simply use arbitrary waveform generator to generate digital profiles at the frequency of the transition between 0 and 1. And then this very precisely generated profiles are directly applied to the qubit. So one saves here additional complication of having additional microwave source for the local oscillator up conversion. And secondly, these pulses, because they're not up converted, they avoid any conversion errors which occur due to the nonlinearity of the mixers. So this makes actually fluxonium with this very low frequency of the transition a very favorable device for doing very high accuracy single and two qubit gates. Okay, so all these nice advantages of having suppressed charge noise and harmonic levels and low frequency, which is very convenient for the transition between ground state and excited state, all this have their price. And the price to pay here is the parasitic modes, which occur in the fluxonium due to the series array of Josephson junctions. If you take a series array of Josephson junctions, they are indicated here by red crosses, and the equivalent circuit is shown here on the right. So these are the junctions, which are basically Josephson elements, IC sin phi for the current, plus the capacitance in parallel. They form kind of transmission line because every island here between the junctions is coupled to the environment. This environment is simply a capacitance or the characterized by energy of removing a charge from the island to infinity. And this capacitance, of course, for any wire is never zero. It's very small, but here it's exactly where this capacitance plays a role. And one can take into account this capacitance, which is in the range of attofarad. Is shown here by the capacitance to the ground. If one looks at this circuit, one can write the equation, classical equation of motion for the phase differences phi n, which are the phase differences on all these different junctions. One finds the set of coupled nonlinear equations, which can be then linearized by replacing sign with simply the argument. Then the system of equation becomes linear, and one obtains then the eigenmodes for the system, classical eigenmodes. Of course, it's not a quantum problem; it's simply a classical problem, electrodynamics. And these eigenmodes are given by this formula. So they are given by the mode has an index n. N is basically the number of half wavelengths along the array. So if the lowest frequency mode corresponds to kind of standing wave, where the wave extends from left to the right, from very first junction to the very last junction, with antinode in the middle and nodes at the edges. Excuse me, I think it's the other way around. With antinode at the edges and node in the middle, if the array is isolated. If the array is not isolated, if the current can flow, then it will be other way around, as I told you. So basically, it determines by the condition for the maximum amplitude of the electric field. If the array is disconnected from the rest of the world, then this maximum amplitude of the electric field occurs at the ends of the array, which means that you will have maximum of the electric field at the ends of the array, and the minimum in the middle, of course, automatically. And if you have now the array connected to the low impedance environment, then of course the minimum of the electric field will be at the end of the array and the maximum in the middle. So it depends on the boundary condition. But nevertheless, this eigenmodes, they have a very generic character, and as you see here, it has the shape of the effective plasma frequency, but now sort of dressed with particular additions of different Josephson junctions. This n actually enters also in the denominator here, multiplied by the capacitance of the junction, and now this factor C0 is quite small. Therefore, the characteristic frequency of the array can be, of the first mode, can be quite high. But nevertheless, if you go to high modes, then there is a saturation of the mode frequencies at the plasma frequency of individual Josephson junctions. So this individual Josephson junction has individual plasma frequency, which is in this units equal to 1. And these different modes, mode 1, number 1, number 2, number 3, and so forth, they go equidistantly in the resonant mode number, of course, this shown here. It's like something like, if you want, the wave number. And this is the frequency. So basically what you see here is the dispersion. And without junctions, if this would be simply capacitances, then these modes will go along this dashed line. But with junctions being here, they will saturate at the plasma frequency of the junctions. And if one plays now with this capacitance basically depends on the size of this electrode. Smaller is the size, smaller is the capacitance. So make this capacitance very small, push the frequency of the lowest mode up, while making the capacitance of the electrode large, push the frequency of this mode down. And what happens in fluxonium qubits is that these modes, they sort of conflict with the modes of the fluxon. They mix with modes of fluxonium device, fluxonium Hamiltonian, because these particular modes are not included in the full spectrum of the Hamiltonian, because in the Hamiltonian this series inductance is approximated simply by lumped inductance element, and interaction with these modes makes the operation of the device often impossible. So one has to make the design such that these modes are really well above the frequency of interest. So we will make the fluxonium frequencies at frequency below the lowest mode shown on this plot. So this is a relevant work, and actually has been realized not very quickly after discovering of the fluxonium, but then people finally analyzed the system. There are a number of papers listed here where this problem was addressed, and now people know how to design the electrodes and what to worry about to make the device working properly. Now, the very smart way of reducing the stray capacitance is avoiding the dielectric. You know that if you make two metallic electrodes, they form a capacitor, and if you put these metallic electrodes on the dielectric, then half of the space is filled with dielectric with epsilon larger than 1, and therefore the capacitance increases. So if you disconnect the metal from the dielectric, then capacitance decreases. And that's something which was discovered in the group of Vladimir Manoucharian very recently. They found the way to etch away the silicon substrate below the device they fabricated. And they were even able to make the device such that the chain of Josephson junctions, which you see here, together with a small junction there, was simply hanging in the air. In this case, the stray capacitance of the electrodes between each Josephson junctions. Now, in this line, there are many Josephson junctions here in series, and between each pair of Josephson junctions, there is a superconducting electrode there. So obviously, in this case, the stray capacitance was minimized, and therefore the modes were really pushed very high up. This made it possible to realize the parameter limit, where the Josephson junction really was very tiny, with the charging energy of the order ratio to the Josephson energy of the order of 1, and quite large, quite small value of the inductive energy compared to the charging energy here, about 1 to 100. And this actually brought this device in particular limit, which the authors called the so-called Bloch-Neum qubit. Bloch oscillations is something you might, or you should actually remember from your solid state physics. So this is the oscillations, quantum oscillations of a particle in the periodic potential, such that depending on the wavelengths of the Bloch waves, there will be basically interference with the reflected waves propagating in opposite direction, and eventually, in particular wave number, you will have the standing wave, which is called commonly Bloch oscillation in the periodic potential. Now, this device was called Blochnium because in the periodic space of quasi-charge, here the states of different charge number of the of charges on the island, on the quantum junction, which is shown here, they were coupled by tunneling from multiple wells. So basically, the state was extending over multiple minima in the potential, and therefore the this device was really different from the devices I discussed before. If you look at the parameter space, this is the ratio of Josephson energy to charging energy. Now, this is the ratio of the inductive energy to the charging energy. And for fluxonium, the inductive energy is quite large, and therefore the point is somewhere here. This is the parameter range of fluxonium. For transmon, inductive energy is 0, so basically you are here, and for charge qubit is also 0 as well. So Blochnium is something in between charge qubit and fluxonium. Now, it didn't deserve, let's say, any credit towards being favored as a hardwire for quantum computing, because its fabrication is very challenging. To reduce the capacitance to very, very small numbers and making the inductance very large is very difficult. Nevertheless, the physics is very beautiful. And if you want to learn more about that, look up this Nature paper published roughly 2 years ago. All right. Any questions to charge qubits, complicated spectrum? My comments. The stuff, the material is not very simple today, but I deliberately make it not simple to keep some of you on board who have potential for that, intellectual capacity, and for those who want to catch up. I think it's rewarding to see something beyond the simple things I discussed before. Какие-то вопросы, пожалуйста? Когда у матросов нет вопросов, как-то похоже, что матросы не достаточно разобрались в материале. Или все просто? Кто-то может что-нибудь сказать?
Простите, а мы можем вернуться назад на слайд, где флюксониум был?
Да, конечно.
Там были графики, да, графики энергии, где были, как раз где вы говорили, вот здесь, следующий слайд.
Еще?
Нет, наоборот, следующий слайд, где вы говорите, вперед чуть-чуть пройти. Вот здесь, да. Вы говорили, что вы не помните, что такое СР, хотя мы его видим на эксперименте. А что такое 0 в 4? Там нижняя какая-то линия еще в нижней части спектра.
Это двухфотонный переход с 0 в 4. Видите, двоечка стоит.
Понятно, то есть эти переходы, они тоже оказывают влияние, заметное?
Ну да, то есть при большой мощности сигнала они видны, то есть многофотонные процессы, они существуют в более высоком порядке по теории возмущения, и их интенсивность слаба. Но тем не менее, вот при выбранной мощности уже этот вот переход был виден здесь, двухфотонный между 0 и 4. Частота получается здесь где-то, видите, значит, 8,5 умножить на 2, все это будет где-то 16, это вот наверху, мы просто не видим на этой картинке. Однофотонный переход туда.
Понятно.
Еще вопросы, пожалуйста.
Да, вот, извините, вопрос есть. А мы можем на предыдущий слайд откатиться?
Да.
Да, можете, пожалуйста, помнить, что вообще у нас происходит, когда у нас вот линии энергетического уровня пересекаются? То есть, что вы рассказывали, я упустил просто это.
Да, ну смотрите, здесь просто, значит, диагонализация, ну, собственно, значение двух гамильтонианов показано. Значит, голубыми линиями показаны гамильтонианы, значит, голого квантового, значит, осциллятора гармонического, да? То есть это основное состояние, и вот дальше мы просто частоту берем вдвое, получается, значит, первое возбужденное состояние, где-то выше там есть второе возбужденное и так далее. Дальше, если мы добавляем теперь, просто складываем с этим состоянием энергию кубита, которая зависит уже от магнитного потока. Вот голубые линии не зависят от магнитного потока, да, а кубитные линии не зависят. У нас получается, соответственно, для первого состояния, значит, вот когда, точнее, для возбуждения кубита это вот оранжевая линия, а когда мы добавляем сюда еще синюю моду, да, которая не зависит, мы просто сдвигаем оранжевую линию вверх. Видите, мы во всем интервале добавили частоту голубой моды к оранжевой моде, получили вот эту оранжевую линию. И дальше добавили 2 раза, получили вот эту вот линию. Теперь, когда у нас возникает уже система связанная, когда у нас есть какая-то связь здесь между этими модами, то у нас они начинают взаимодействовать. И вот фактически вот в точках пересечения происходит расталкивание уровней, то есть происходит как бы то, что называется avoided level crossing. То есть в случае взаимодействия двух квантовых систем, значит, возникают 2 состояния, значит, с симметричной и антисимметричной волновой функции, состоящей из компонентов, взаимодействующих компонентов связанной квантовой системы. И вот эти же пересечения, то, что я говорил, они видны вот здесь, видите? Вот резонатор пересекается с линией кубита, и выражение снимается. Вот. Это выражение снимается на всех более высоких пересечениях, но здесь пока вот видно только одно нижнего уровня, так сказать. На самом деле, если включить мощность побольше, то вот здесь появится, значит, на частоте 8 плюс частота кубита, появится вторая мода резонатора, и на этом рисунке не видна, потому что это будет 16 ГГц. Вот. И там будет тоже, значит, расталкивание уровней. В этом был ваш вопрос?
Да.
Угу. Хорошо.
Спасибо.
Еще, ребят, вопросы? Хорошо, давайте сделаем перерыв. Значит, мы приплыли вот к какому слайду сейчас. Вот. Ну и я потом еще с него начну, прокомментирую. Будем двигаться дальше. Так, давайте 10 минут перерыв. Начнем в 12:02.